Hello and welcome back to a fun new chapter of methods. Wow, we are powering along. Chapter 10 already. Cool, cool, cool. This chapter is all about the applications of differentiation, which is good to see that we are actually going to be doing this, looking at some maximum and minimum problems and things like that. First, we need to have the chat about tangents and normals. Again, this is stuff that you guys did in year 11, so there shouldn't be any surprises here with that. Essentially, what you will get often is a coordinate, or you need a point on a function. So you'll have x1 and y1 values, so coordinates on a curve. And it says if f is differentiable at x equals x1, so at this particular point, if it's differentiable, then the equation of the tangent at this particular point is given by this rule here. So that's useful, and that's used all through this exercise. Essentially, as we know, f dash of x1 is basically finding out what the gradient is of the original function at that particular point. Yep. So let's have a look here. It says find the equation of the tangent to the curve at the point x equals 1. Cool. So what we need to do, first of all, is find out its corresponding y coordinate. So we can substitute that into the function and calculate that. So 1 getting substituted into there comes out as being 3 over 2. So we've got the coordinates, the x1 and y1 values of 1 and 3 over 2 as written here. And that is the point of the tangent that we're going to be working out. Yep. Next, we need to work out what the derivative of this function is here, the original function. So we know how to differentiate things. We've got the derivative here, it's 3x squared plus x. Cool. So if this is the point of the tangent, and we want to get the equation for the tangent, we know its x value here, its x coordinate is 1. So we're going to substitute 1 into the derivative, and that will tell us what the gradient is at that particular point. Yep, so the gradient of that tangent. So substituting x equals 1 into the derivative, we get that the gradient of the tangent is 4. Cool. So ultimately this f dash of x1 is going to be 4. And you can see, writing out the equation using this rule here, y take away y1 equals f dash of x1, x take away x1, writing out the rule and substituting in the things we know, that f dash of x1 is the gradient at that particular point. So that's where the 4 comes from. Yep. Also, writing out the rule, here is the y1 value we worked out, and here is the x1 value we worked out. Yep. So really the rule is useful. Tick. You can simplify it down, as you can see here, and writing out the equation of the tangent to the curve at that particular point is y equals 4x take away 5 over 2. Cool. Next thing that you need to know, and I'd be highlighting this in your fun notes, is the normal of a curve. So essentially it says here the normal of a curve is the line that passes through the point and is perpendicular to the tangent, so at a 90-degree angle to the tangent. So, recalling fun facts from chapter number 2. It says that two lines with the gradients, okay, if you've got gradient m1 and m2, they are perpendicular if and only if when you multiply them together, they equal -1. Cool. So using that rule, it says a tangent has if the tangent has a gradient of m, so if you know the tangent, the gradient of the tangent, you can work out the normal, the normal's gradient by having -1 over m. Yep, because that way, when you multiply the two of them together, it will come out to being to -1. So again, this is very, very useful. Sometimes people forget that. Yep, I would be making a note of it. Oh, cool. Example 2 is actually asking us to do this. It says here, find the equation of the normal to the curve with the equation here and at the point 1, -1. Yep. So this time they've given you the x and y coordinate. If they just gave you at x equals 1, you'd have to substitute it in and find out what its corresponding y value is. They were nice here. They gave you that additional information, so you don't need to work that out. So to calculate the equation of the normal, we need to work out what the gradient is at this particular point, x1. Yep. So we're working out the derivative here. Derivative of this here is 3x squared, take away 4x. And so what you would do to work out the gradient is you would substitute in 1 into the derivative, and you'd get the m value. Yep. So let's just write that down. Substituting it in, you'd get m is equal to, imagine that says m. No, actually that's horrible. M is equal to, okay, so 1 squared is 1, 3. 3 times 1 is 3, take away 4 times 1. Okay, it's going to be negative 1. So m is negative 1. Yep. But you're after the gradient of the normal. So remember, it's negative. The rule is negative 1 over m. In this case, m was negative 1. So you're going to have negative 1 over m, which is where you get the negative 1 over negative 1. Negative 1 over negative 1 is just 1. So the gradient of the normal is positive 1. Cool. So once you've got the gradient, obviously using the rule here, that value goes in front. Writing it all out, here is your y1 value, here is your x1 value. Yep. As you can see, they've been substituted in. Simplifying things down, you get the equation of the normal at that particular point is y equals x take away 2. Cool. This is fun. What's the next one? Oh, same thing, but just a little bit different equation here. Yep. So again, finding the tangent of the curve with the equation at the point where x equals 4. Again, they've only given you the x coordinate. To find out the corresponding y coordinate, what am I drawing here? So you know that it's 4. To find out its corresponding y coordinate, you're going to substitute in 4 into the equation. Doing that, you get y is equal to 0. Cool. So you've got your x and y point. Again, you need to find out the derivative of this here. So derivative in this particular case is calculated, and you're able to do that. Happy days. To find out the gradient when x equals 4, you have to substitute in 4 into the derivative, and we get that the gradient is equal to 2 at that particular point. Yep. So again, write out the rule that's listed here, there, and we've got the gradient in front of the brackets here. This here is the y1 value, which we calculated here, and this here is the x1 value. Simplify things down, you get that the equation of the tangent is y is equal to 2x take away 8. Cool. So again, relatively straightforward. Yep, just make sure you're accurate with your calculations. Oh, this can be done on a calculator. Cool. And you might like to actually have a try of doing this one. That particular question that we did above, you could do it on the calculator. So what it says here is go into the main section, and if you've typed in that into the calculator, you could highlight it, and you could copy and paste it. Then go to interactive calculation. You go to line, and in there's tan line, which I'm assuming is for the tangent. Yep. It looks like there's also normal in there, which could be useful as well. Yep. So in this particular case, a little box comes up. You put in the equation, which you can press paste if you've copied it, or you can type it out in there. The variable is x. Obviously, if it's something else, you'd change it. And if you want to find out what the equation is, and at x equals 4, you put the point, the x coordinate, in there. Happy days, press the OK button, calculator does its thinking, and will spit out y equals 2x take away 8. Yep, as you can see there. Just see it says 2x take away 8, it says write your answer as an equation, so y equals that. Yep. Also, it says you can obtain the tangent line by sketching the graph, so going to the actually graphing section and have it. So you could have graphed this, and then actually go analysis sketch tangent, and it will sketch the tangent on there at that particular point, which is pretty cool. Example 4, again, same difference, applying the rules, except we're doing it with trig. Again, we've got this time they want to find a tangent. of y equals sine x at the point x equals pi on 3. Okay, so again you need to find out the y coordinate when x equals pi on 3. So a matter of substituting that into the original equation, we get that y is equal to root 3 on 2. So here's our coordinates, x and y values. We also need to find out the derivative of y equals sine x. Hopefully by now you realize that it is cosine x. Yep. So we need to find out at this particular point, when x equals pi on 3, what the gradient is. So we substitute that into the derivative. Cosine pi on 3 is a half. So there is the gradient. Okay, so you've got your x1 value, you've got your y1 value, that's a y, and here is obviously your gradient. Writing out the rule again, plugging in the things you know. The thing in the front of the brackets is the gradient, which was a half. Here's the y1 value, here's the x1 value. Yep. Rearrange things, simplify things down, you can get something a little bit neater there, which is the gradient of the equation of the tangent. Yep. This one here, same difference again, except this time they're asking for both the tangent and the normal. Yep. So we've got an equation. Also we've got point, so it's pi on 2 and 0. So again, you'll need to work out the derivative of this here. Derivative of negative cosine x is sine x. Yep. So finding out what the gradient is at pi on 2, we substitute that into the derivative. So sine pi on 2 is 1. Again, you've got your points, you've got your gradient, plug it into the rule, you can get the equation of a tangent. Next thing is, it says the gradient of the normal is -1. Yep. So again, the reason they've got that, remember, it's -1 over m. We worked out the gradient of the tangent. Yep. So it's 1. So the gradient of the normal is going to be -1 over 1. -1 over 1 is -1. That's how they get the gradient of the normal, because you already had the gradient of the tangent. Yep. Alright, so we've got the gradient of the normal. In this particular case, we already had the point. The equation is just going to be the same, except that's going to change there. Simplifying things down, you get y equals -x plus pi on 2. So you've got both the, that's the normal, and here is the tangent worked out. Cool. It says here, cool, there's examples where there's two situations where we can view a graph as having what's called a vertical tangent, a tangent that goes straight up or down. Cool. So it says here, find the equation of the tangent to this equation at x equals 0. Yep. So again, if you think about sketching x is 1 over 3, here's the equation. Cool, it says if the derivative of this particular function is not defined at x equals 0. So again, if you were to differentiate that here, that looks like it's one of those truncus again, where there is an asymptote at x equals 0, so it cannot be differentiated at that particular point. Yep. So even though like we can't work out what the gradient is at that particular point at x equals 0 because it's not defined, you can see clearly that it is continuous to the original graph at that particular point. Yep. So in this particular case, it's clear that f is continuous at x equals 0, and that f, the derivative f dash x as it approaches infinity, as x approaches 0, then you can say that at this particular point at 0, x equals 0, it's going to have a vertical tangent. Yep. Likewise, same difference here. Here's a different equation, x equals 2 over 3. Again, the derivative of f is not defined at x equals 0, as it says here. However, you can see it is clearly continuous at that point. I could draw that point of the graph without taking my pen off the page. However, it's a cusp there. It's really, really sharp at that particular point. Yep, at x equals 0. So again, Due to the nature of it, you can see it's continuous, it, but you couldn't find the derivative when x equals 0. So in this particular case, again, it's going to have imagine that's a straight line, a vertical tangent at x equals 0. Yep. Here are some section summaries. That's really important. We use that all this exercise. Get that into your brain. And also this one I have alluded to as well. Very important. Hey, thanks again for listening. Bye for now.